Alright guys, I'm on the last part for Riemann sums, and we're gonna start transitioning from problems on that sample worksheet to actual problems in your book. So let's go to page 257, and we're gonna go full screen this time, so hopefully it's easy for you guys to see. And let's read over something that seems familiar, but this time doesn't have like the steps laid out for you. So this is inflating a balloon, and let's read a spherical balloon. So a sphere, it's like a 3D circle balloon, is inflated with helium at the rate of 100 pi feet cubed per minute. So that's a rate right there. A rate of what? We don't know. Or maybe we can define that in just a second. The first question is, how fast is the balloon's radius increasing at the instant the radius is 5 feet? Okay, so you can do this however way you want, but let's see if I can. Oh, sorry, I'm trying to get this to be at the top of the content here, or the top of the video here, okay? Okay, so if we want to do this as steps, like sequentially, you don't have to do this, but again, I like the organization that I got from the worksheet. So this is namely for, let's see, this is namely for part A. First step is to define any variables that we have. So R, I know it's going to be radius. I know time is going to be involved because it has something to do with minutes, okay? Time is minutes, or time. Or radius is in feet, sorry. And then T is time, I'm sorry, but it's in minutes. It's in minutes. So another thing is volume, because I could tell it's feet cubed. Immediately that tells me that it's the volume of the balloon, or the spherical balloon. That's going to be in feet cubed. Okay. Let's see, I think step 2, let's go back to the organization here. So let's go back to the worksheet here. Variables and what they mean. So we talked about that. Then there's rates of change, known and unknown. So, and it does say that the radius, we are looking at the instant where the radius is 5 feet. So let's say that this is 5 feet. Okay. Some other things that we're talking about is how fast is the balloon's radius increasing. So it looks like how fast is dr/dt increasing. And that's what we don't know. But we do know that how the volume is increasing is 100 pi feet cubed per minute. So that's 100 pi. That is a constant number because pi is 3.14 approximately. And then it's feet cubed per minute. So that is a good place to start for the units. I think that's about it. It doesn't really talk about anything else. And then step 3 is to maybe just draw it. You don't have to, but it's a spherical balloon. So there it is. Imagine that's in 3D. So I'll put it like a little bit of shading there. I don't think that really conveys it really well, but let's say it's a balloon. I think it's being inflated. So this thing's being inflated. So it's from the center, it's sort of increasing to a slightly bigger balloon, right? So we're going at the point where the radius is going to be approximately 5 feet. And then the rate at which it increases, which is this arrow, dr/dt, is what we don't know. But just in general, like, I don't know how to convey this, but not just like the height, but the whole thing, in which the volume is increasing, right? Kind of we're looking at dv over dt. And we're looking at it at the instant when the rate of the increase is 100 pi feet cubed per minute. Okay, so I'm looking at a spherical balloon. It's increasing its radius and volume. We don't know, so at the instant where the radius has reached 5 feet long, and the rate at which the whole spherical balloon is increasing at 100 pi feet cubed per minute, so in 3D it's getting that big. How big is the radius, the rate of the radius increasing? Let's link this. Basically, just tell me what the volume of a sphere is. If I remember correctly, that's 4/3 pi r squared or cubed. Let me see. Yeah, I think it's 4r pi r cubed because it's 3D. Okay. And then to link time into this, we're gonna take the rate at which all these volume and rate changes with respect to t. So it's gonna be, we're gonna take the derivative of all of these guys with respect to the variable of t. So that's the equation we want to work with. Step 4 is actually differentiating that. Okay, actually let's put this down here. So step 4 will then be to actually take the derivative of this. So on this side it would just be dv with respect to t, because the derivative v would be 1, but then you have to do the derivative of the inside function, so that'd be derivative v with respect to t. And then this would be 4/3 is constant times 4/3 pi. That's all constant. You're going to take the derivative of the only variable that's there, which is r cubed. It's implicit differentiation because we don't know what function of time is within r. So we're first going to take the derivative of the outside function, which is r cubed. That would be times 3r squared, and then times, so we did the derivative of the outside function. The derivative of the inside function is whatever is hidden within r that is a function of t. It could be like t squared plus 4t minus t. I don't know what it could be, but that's going to be dr times dt. Let's simplify that to dv over dt is equal to, these will cancel out. So I'm going to have 4 times pi r squared times dr over dt. And step 5 is to put in the known values. We are searching for dv over dt. And we have values. We're talking about the instant where the radius is 5 feet. And dr over dt. Oh, I'm sorry. So we're looking for dr over dt. We do have dv over dt already. I do apologize. Because the radius, we know, we want it to be at the point where it's 5 feet. It's expanded to 5 feet. And we also know that the rate of the volume changing is 100 pi feet cubed per minute. So what we're actually looking for is how fast the rate of the radius is changing. So let's put in some values here. So in place of dv over dt is going to be 100 pi feet cubed per minute. I do like to include the units. 4 pi times r squared, which is going to be 5 feet squared times dr over dt, and we're going to solve for dr over dt. We're going to divide both sides by 4 pi to isolate dr over dt algebraically. This is going to be 5 feet squared, which is 25 feet squared. That's going to cancel out, and then you're in whatever you do to one side of the equality sign, you have to do it to the other side of the equality sign to make both, to continue to make both sides equal. Sorry, so that's, so I guess what I didn't do was multiply this out. 4 pi times 25 feet squared. If I actually did the math to see what that equals, 4 pi times 25 feet squared should be 100 pi feet squared. That looks almost coincidental, but it's very intentional the way this problem was written. So 100 and the pi are going to cancel out. The units of f feet squared are going to cancel out. But up here it's f cubed, so that's just going to go down to an order of magnitude of 1 foot squared. So what we're going to have is not 1 foot squared, but 1 foot over 1 minute dr over dt. And does that make sense? Yes, because again, radius is only in feet, not feet squared. Radius is two-dimensional. It's flat. We're talking about the radius, just flat. We're not talking about 3D. In 3D, how everything is expanding. We're just talking about how the radius expands. Okay, you can look at that as being one way, whether it's one way on the paper, one way towards you, but it's not simultaneously growing in like the x, y, z axis all at the same time. Okay, we could just look at radius in 2 dimensions at a time. So we can look at it like going it just one way here, or we can look at it going one way here, 3D towards you, one way at an angle, but one way at a time. Volume is all 3 ways in 3D space, how fast everything is moving in that instant. Okay, sorry, so in case my language kind of it's kind of confusing you. So we just know radius is a 2-dimensional measurement. Okay, at a time, at a specific time. So the radius changes 1 foot per minute, not 1 feet squared. That'd be area, and that'd be and not feet cubed because that'd be volume. We're talking about just pure radius. That's good. Okay, so that's just for part A. So let's go back really quick. How fast is the surface area increasing at this time? Okay, so let's go back really quick. Okay, so we're talking about how fast the surface area is increasing. Let's try to break this down again. Step 1 is now we're talking about the surface area. Surface area. And if we talk about surface area, that I think that's going to be in feet squared. And they're actually asking how fast the surface area is increasing at that instant. At the same instant, you're talking about the radius, which is, sorry. So you know what? Let's rewrite this really quick. Sorry, that's not the format in which we were doing that. We're doing it like variables. So the variables that we have are the radius. So that's not different. The radius, that'll be in feet. We're talking about now a new variable. I'll just call that SA for surface area. You know what? I'm going to shorten that down to just being an S. Singular letters will be a lot easier. Surface area. Okay. And time. Time again will be, we're using time in minutes here. And surface area would be feet squared. Step 2 will be any rates of change to consider. We do want the rate of change for the surface area. Okay, rate of change for the surface area. dr over dt is the rate of change for the radius. And that'll be about it. Step 3 will be a picture. It's a little harder to convey, but again, you have a sphere here, a spherical balloon, and slowly the radius is growing out to a bigger spherical balloon. Okay, and we're talking about it at the time the radius is equal to 5 feet, and the what is it, dr over dt Let's see, d over dt, we actually determined from the last problem at that instant, it's 1 foot per minute. Notice I haven't talked about the volume at all. And you'll see why in just a second. And then really what we're trying to look at is, I don't know if like we do like a little zoom in, but how big is the surface area increasing? That's like only in 2 directions. I don't know, it's kind of hard to convey, but like in the arrow of like, I'm just looking at just the surface, so not like in 3D how the whole sphere is expanding outward, but we're looking at it like just on the surface of the sphere. How big, how fast is it kind of expanding in two directions at the same time? Okay, but just on top of the surface of the sphere, not the actual like the whole depth, the height, and all that pure 3D how it's expanding outwards, but just on the surface, how is it kind of growing? So I don't know how to convey that, but more clearly, but ds over dt is the question. And the reason why I didn't have volume is because when you think about the surface area, the thing that links everything together, the surface area of a sphere, its equation is 4 pi r squared. It doesn't include volume in there anywhere in here, so I don't need the volume equation at all. It doesn't need to be involved at all. I could just solve this problem using the surface area, or the equation for surface area for a sphere, which is S, or the surface area is equal to 4 pi r squared. And then we're going to take the derivative of this whole thing. So that includes the dimension of time involved in this equation. Okay. Step 4 is to take the derivative of this, which would be ds over dt is equal to 4 pi is a constant, so we're going to take the derivative with respect to time of r squared. It's going to seem very familiar. So ds over dt is going to be equal to 4 pi times 2r to the first power times dr over dt. Okay, we are trying to find how the rate of change of the surface area, so that's still going to remain as the variable that we don't know. 4 pi times 2, that's 8 pi times r. R is going to be 5 feet. And we do know the rate at which dr is changing from the last equation. That is 1 foot per minute. Sorry, so I'm kind of simultaneously going into step 5 here and just solving it, because I just want to kind of get this done. I do apologize. So ds over dt is going to be equal to 8 pi times 5, that's 40 pi, and then the units are huge. It's feet times feet over minutes. So that's feet squared per minute. And then that should be my answer. Does the unit make sense? Yes, it does. You can see that's an area, feet squared, changing per minute. So that totally makes sense for the surface area changing. Okay. All right, guys. That's how you take care of 11A and B. You guys will probably do this in less steps than I did, or not even any steps. You guys could have done in any order you guys wanted, but I did it in a more formalized way to do that. Solve for these related rates problems. Okay, guys. Thank you guys so much. That's it for related rates. Let's go on to Riemann sums, and I will see you soon. Bye.